Hi everyone, welcome back. So I'm a little nervous in the first video, but I think in this video I should be much better. So in the last one we have proved like the link flow homology can. So Arch van Zabel proved the link flow homology can determine the certain norm, and we gave the bounds for the strong four-ball genus in terms of H function. This seems really a good news, but they're very hard to compute in general or in practical because the definition is using some holomorphic disk. And if we want to compute them, we may need to count the holomorphic disk, which is a very hard task. However, the good news is like for some families of links, these invariants, including the H function or including the invariant we need to compute the certain norm. For these families of links, they're both computable from their Alexander polynomial. There's a combinatorics algorithm to determine this invariant from Alexander polynomial. So this seems really a very good news. And these families of links is what we call L-space link, and is also the key point in the second session of this talk. Before we talk about the definition for L-space link, we may need to first of all see the definition for L-spaces. L-spaces is the concept for a three-manifold M, and we say a three-manifold M is an L-space if it's first of all a rational homology sphere, and then it needs to satisfy the link, the three-manifold invariant we have defined in the first session. HF minus is exactly generated by one element as an FU module for each spin C structure. T. This actually is an analog for S3. If you remember, HF minus of S3 is exactly FU, and because it only has one spin C structure. So S3 is an L space, and all length space are also L spaces. That's where the name L space comes from. So then we can define L space links. We say a link L is an L space link if for all large surgeries, they are all L spaces. So you need this surgery coefficient DI are sufficiently large, and you need to check for all large surgeries. So from this definition, it seems not easy to determine whether a link is an L-space link or not, because you need to check all large surgeries. However, there's an induction technique you can use. So this is not a very horrible or impossible task to check whether a link is an L-space link. For example, the trivial example is the unlink, which is an L-space link, and also the two-bridge link I drew in the first video is also a family of L-space links. And actually, more general is correct. There's a bigger family which are all called edge break links coming from some equation. There are also L-space links. So why L-space links are interesting? And why we care about L-space links? One reason is for the computation reason, as we mentioned before. So for L-space links, this HF minors or this link invariant, HFL hat or this H invariant, they're all computable. For example, the theorem of Gorski and Brodik saying like the H function for L-space links is determined by the Alexander polynomial of the links and its sublinks. Meaning like if you know these Alexander polynomials, then there is a formula, there is an explicit formula to compute the H function. So it's very clear and it's very computable. And so for the certain norm, we prove like if we have two component L-space link, then this link invariant we need to determine the certain norm, and also we prove the certain norm are both determined by this H function, and hence they're also determined by their Alexander polynomial. So actually for two component L-space links, the question of certain norm is determined, meaning like the Alexander polynomial will give you explicit answer for the certain norm. And these are all for the computation reason why we care about L-space links. But the interesting thing of L-space links is not only about computation. There are a lot of interesting results for L-space links we want to talk about today. Because instead of spending the time on the proof details, I maybe want to spend more time on the interesting properties or interesting results for L-space links so that people can understand why we care and why we do things along L-space links. So go back to G4L, there's a straight corollary saying like if you have this link, you with the assumption like it is a slice link and a plus it is an L-space link, then actually we can say we can prove it's the unlink. The idea of the proof actually is not hard. If it is slice, means the G4 strong, the strong for genus is 0. And if you remember the bounds for the strong for genus in the first video, it is like what I wrote here. Then the right-hand side is always 0 because GI is always 0. So you get the H function for this link is the same for the H function of unlink. And you need to do some work to determine the certain known for this L is the same as the certain known for this unlink, which will prove the link is exactly the unlink. So here, this L-space link assumption actually gives you some abstraction for a link, for a non-trivial link to be a slice link or not. And another interesting result relating to L-space link is the relation between H functions and the Milnor numbers. The Milnor numbers here, I will use the Sato-Levin invariant or the Milnor triple linking number. So, for example, with the joint work in the joint work with Gorski and the Moon, we prove like if we have a two-component L-space link with linking number 0, then you can prove like the Sato-Levin invariant of this link is can be written as the sum of the H function for the link, subtract the H function for the component L1 and the H function for the component of L2. So you can write the Sato-Levin invariant as a linear combination for this H function of the link and its sublinks. And maybe for some of you, maybe it's good to record the definition for Sato-Levin to help you remember. So if you have L1, it bounds a cipher surface sigma 1 in S3 and the same for L2. The cipher surface sigma 1 has empty intersection with L2 and the sigma 2 has empty intersection with L1. Then you can consider the intersection of sigma 1 and sigma 2, let's denote it by L12. So the Sato-Levin invariant is defined as the self-intersection number of L12. With the help of the relation to the H function, we can prove like if you have a Sato-Levin invariant equals to 0 and you assume both of the components are unknot, and actually then you can confirm the link is just the unlink. So you can detect this unlink by using the Sato-Levin invariant. And then in the joint work with Gorski, Liebman, and Moon, we generalize the relation with Sato-Levin to the Milnor triple linking number, meaning like if we now have a 3-component O-space link L with 3 components, and we assume it's Brownian, means every proper sublink is the unlink, then we can prove like the triple linking number of L, its square equals to the sum of H function of L minus the H function of the unlink. So this formula actually can be generalized for any 3-component L-space links. We can throw away the assumption of Brownian, but the formula is kind of complicated and also not very practical when you compute. So, so I add the assumption for Brownian and make this formula more explicit and easier to observe. And you can get some feeling between this H function and this Milnor triple linking number. As the same story for the Sutter-Levin, if we assume the triple Milnor number equals to 0, then actually we can prove the link actually is the unlink. So you can detect the Brownian O-space link to be an unlink by observing the triple linking number to be 0 or not. Then another interesting part for the O-space link is to see the surgery three-manifold. As we said before, we want to figure out what we can say about the link if we know some information of the surgery three-manifold, or what we can say about the surgery three-manifold if we know some information about the link. So now if we know, so if we have this surgery three-manifold, we're wondering when this is an L space. So by definition, if all surgery coefficient di are sufficiently large, then it's definitely an L space, just by definition. However, we don't know for other surgery coefficient, right? In the case of the knot, say if L is a knot, then the answer is pretty clear. You say the surgery is an L space if and only if the surgery coefficient D is greater or equals to 2 times genus minus 1. Here we only care about the integral surgeries. Usually you can also consider rational surgeries, but it's not, but I won't talk about it here. And if you go to more components, say L is a 2-component link, then this question is hard enough. For example, for this 2-component link, you have D1 surgeries here, D2 surgery coefficients there. So by the definition, you know when D1 and D2 are both very large in this quadrant, this will give you some L-space surgeries. But you don't know about other surgeries in other place. However, there's some nice result saying information about the link by observing the surgery three-manifold. For example, we prove like if you have a 2-component L-space link, and furthermore, you assume this is an L-space for D1 sufficiently negative and a D2 sufficiently negative, that means you can find a point here which give you an L-space surgery. Then you can do some link detection proving L is the half link. And another interesting result is if you have a 2-component L-space link with linking number 0. Oh, sorry, with linking number L. And you furthermore assume Li, both of these components are on knots. Then if you can find one surgery candidate here or here, saying if you have a surgery, which is an L space, for some D1, D2 is negative, meaning you can find a candidate in the 2nd quadrant or in the 4th quadrant, then you can detect actually your link is the torus link T2 to L. So that gives you some link detection result by observing whether your surgery three-manifold is an L space or not, regarding some specific surgery coefficient. I think personally, I like this kind of result because they're nice and neat. So now, yeah, that's what I'm going to say about interesting result relating to L space link. At the end of this second video, I want to go back to the bounds of the four-ball genus and show the examples carefully. So this example is a family of the two-bridge link I drew at the very beginning of the first video. It's a family of two-bridge link with K full twist there and a K full twist on the right. And we say the strong four-ball genus for this link is K. And now I want to use the genus bound we have in terms of the H function to show why the strong four-ball genus for this family is really just a K. So you can see from the picture like this L1 and L2, they're both on knots. So they should bounce disk sigma 1 and the sigma 2 inside S3, though these two disks may have some intersection. So then you push them inside B4, and then you have K positive crossings for this K full twist, and K negative crossings on this right. So by using the technique we have said before, now you can add a tube to connect each pair of positive crossing and the negative crossing, but now you need K tubes. That means I can construct the disjoint surface with the total genus as K. So you get a G4 strong of this link is smaller or equals to K. That gives you some upper bound by constructing the candidates. Now you're wondering what's the lower bound, and then the lower bound is what we need from the H function. If we get the lower bound is the same for this upper bound, then we win the games. We know the strong four-ball genus is exactly K. So if you remember, this lower bounds for the genus come from the H function. So this family of two bridge link actually is an L space links. So if we know their Alexander polynomial, we can compute its H function. The H function looks like the fingers here. Since the genus is always non-negative, so actually we only care about the H function in the first quadrant. You see here the H function takes value 0, and then 1, 1, 2, and then a 0 is the ceiling of K over 2. And the coordinate for the first 0 is 0K. And it's the same for this horizontal direction, and for this 0, the coordinate is K0. And then you see like along this diagonal, I use another color. Along all this diagonal, the H function is always 0, but under this diagonal, the H function is always non-zero. So this diagonal above it, H function is always 0. And below it, H function is always non-zero. Why we care about the place where it's 0 or non-zero? Because if you remember this inequality, HS minus H on link is smaller or equals to FGISI. If you remember this inequality, you make all SI equals to GI, then the right-hand side is 0. For this unlink in the first quadrant, this constant is also always 0. Then you also know this H function should be non-negative. So we care about, so we know, so from this inequality, we get like H of G1, etc., Gn equals to 0. So the place of these two poles of candidates of general should only lies inside the place H always 0. That's why we care about where your H function is 0 and where it is not 0. So your two pole of this integer should be somewhere here. And that means your G1, G2 plus G3, etc. plus Gn should be greater or equals to K from this picture, because the diagonal always has the sum as K. And that's give you the lower bound. And that's why we get the strong four-ball genus for this one is K. And then for the next example, it's also very interesting. We start with the Whitehead link here, and another unknown component. But then we do PQ cables on this unknown component. So the other components becomes the torus link TPQ with P strands and a Q full twist. So for this link, we called it WHPQ. We're wondering what's the strong four-ball genus for this link. There we can find upper bound by constructing some surface. This is a disk. This is a knot, so it bounds a disk. And this is the torus knot. It bounds a cipher surface with genus P-1, Q-1 over 2. But they have intersection. So we can still do the same game by pushing them in before. And here it corresponds to P positive crossings. And here it corresponds to P negative crossings. So we can naively add P tubes for each pair of intersections. So that will give you the candidates of P-1, Q-1 over 2 plus P. That's one upper bound. But if we are more careful, we don't need to add P tubes. We actually just need to add 1 tubes. We actually just need to add 1 tubes to connect the whole strands inside this 1 tube. And then we give a candidate So this is plus b. Then we get another candidate of surface with p minus 1, q minus 1 over 2 plus 1. So this is much smaller. Now we want to see whether we can get a lower bound, which is the same as the upper bound. So we compute the h function for this link. This link is still an L-space link when PQ is large. So if you compute the h function for this link, it looks like the finger here. We still care about where the h function is always 0 and where it is non-zero. It turns out like all these shapes above the stairs have h function equals to 0, and he here has h function equals to non-zero. So, and this corner coordinate has p minus 1, q minus 1 over 2, 1. And this coordinate has p plus p minus 1, q minus 1 over 2, 0. So this corresponds to the bigger genus we construct. And this corresponds to the smaller upper bounds for the genus we construct. And we know like G4L is greater or equals to p minus 1, q minus 1 over 2 plus 1, and also smaller or equals to the same number by construction. So that gives you inequality. That gives you equality at the end. The reason why I think these examples are interesting is because so far we don't have examples of L-space links such that this inequality is sharp. All the examples we have so far is this lower bounds for the h function and upper bound from construction, they're the same. It's like the behavior of the knot. If you have an L-space knot, then we know like G3L equals to G4L and equals to the place h function stops to be 0. So we're hoping like maybe such phenomenon also holds for links. That's one thing. That's one thing we don't know yet, but we hope that's correct. And the other thing is the thing we mentioned at the first in the first video is to compare the strong four-ball genus and the weak four-ball genus of L. Usually, like we say, they could be very different, and the difference could be very large. But we hope, like for L-space link, these two genus should be the same. And there's a reason to believe so, and also there's some way to deal with it. However, the technique we use to prove the lower bounds for the strong four genus does not apply to give a bounds for this weak strong four-ball genus because of some technical reason. So we need to change the way to prove it, or we need to change the technique. And we think this also holds for L-space links. And thank you very much for your attention. And I think that's all the content I want to show you in this session. And also thank you for the organizers' invitation again. See you around or maybe in the office hour.